Hello again, everybody. Here we are, getting ready to do a little more physics. So today we're going to start something new. We're going to do circles. This will be just the beginning. Some of the things we'll talk about, we'll do some amusement park rides. We'll have cars going around circles and curves. We'll talk about planets a little bit. Now technically, most of the planets don't go in circles, but most of them are very, very close to that. So we'll put all this together in the circles category. Um, so let's just dive right in. There'll be a fair amount of stuff I don't actually write down, so be paying attention. If I say something you don't see, write it down as well. Let's just talk about some general circle things. Let's imagine a guy, looks kind of like a physics teacher maybe, spinning something around his head. Let's have a look at this from the top. From the top, we have the little m in blue for the mass that he's spinning. We have capital T for the force of tension in the string. We have r for the radius. And finally, we have the velocity. Now, the velocity is a little odd. You may think that, well, why is it out in that direction? But let's think about this. Let's imagine right at that instant where these pictures are taken, we cut the string. Okay? And if we cut the string, what's the ball, I don't know, ball of yarn? I can't tell what that is. What's that going to do when there's no more string to pull on it? So if he's spinning it around, and let's put him out in space so there's no other forces. Okay? If he does that, the ball's just going to go in a straight line. It's going to just take off and keep going, which means that it has a velocity off in that direction. Now, if the ball were spun around a little bit more and in a different direction, the velocity would be somewhere else. Okay? It would point a different direction. Let's have a look at this. So I've got a little demo here. I've got a table that spins, and right up here I have a little ladybug on it. So I'm going to get the table spinning. So notice what's going on. All that we're looking at here is the velocity of the ladybug. So if we imagine that the ladybug flew off, like jumped off at any second, that ladybug would continue in a straight line whatever direction she was going at the instant she jumped. Does that make a little sense? Not a big jump, just a little let go. So right here where the ladybug's going up, the ladybug would go straight up and come straight down. If we wait till the ladybug gets to the top, the ladybug would shoot off to the left, right now, off to the left in a straight line. Okay? Does that make sense? That's a little tricky, but hopefully not too awful. So, jumping back here, we've got all these things. Now, the mass is going to go in that circle. The tension will point towards the center because it's a string, so it's always pulling towards the middle because that's where he's holding it. And then R and V go around in circles. Couple things as we start doing some numbers. Let's talk about time. That's the easiest one. So what we've got first is something called the period. The period is how many seconds it's going to take to make one circle. All right? So think about this. The period is how many seconds per spin, or seconds for every spin. All right, remember, in our units, we always want to stay in seconds. Okay? The frequency is kind of the backwardsness of the period. The frequency is how many spins it does in a second. So period is seconds per spin, and the frequency is spins per second. Period we're going to use capital T on for, and frequency we're going to use a small f. All right, let's do a quick little example. So let's make this easy. I'm going to go up here and just grab a color. If we go from right here all the way around the circle, like this, and back to here, in 1 second. Okay, right here, 1 second. All right, so it takes 1 second for every spin. All right, 1 second per spin. How many spins are we going to do every second? Well, that's easy enough, I hope. We're going to do 1 spin per second. Alrighty. Now, let's make it a little bit harder. What if we're over here and we go around this circle 2 times, or no, I'm sorry, it takes 2 seconds to go around. So starting here again, I'll go ahead and change colors. We start here, in 1 second, we go to here, and then 1 second, we go around to here. Sorry, I got a little closer to the middle. So it takes 2 seconds for 1 spin, 2 seconds per spin. Okay? So the question is, how many spins do we do every second? How many seconds per spin? That's going to be our frequency. How many seconds do we do per spin? We do half of a spin per second. I'm sorry, I just said that backwards. How many spins per second? Okay, half of a spin per second. Let's turn it around. Now, let's go down to our third one here. What if it takes half of a second to go around? So 1 full spin in a half of a second. All right. The question is, how many spins do we do every second? Well, we do 2. All right, we'll go around twice in 1 second. Now here's the cool part. The period equals 1 over the frequency, and the frequency equals 1 over the period. That has to be that way if you just do the algebra. So if we go over here, and if we have 2 seconds, and we take 2, and we plug in 2 seconds right here, all right, and we do 1 over 2 seconds, what do we get for the frequency? We get a half, right back up here. Same thing over here, all right? We can go the other way. Let's take 2 here, all right, for the frequency. So we'll plug in our 2 right there, 1 over 2. What do we get for the period over here? We get a half. So there we go. Quick example, we're going to use that from time to time, not too hard. The good news is also this equation is on your AP sheet. Okay, so you don't have to remember it, but it is pretty easy. Alrighty, so that's our time stuff. Next one, let's do velocity. So we did time first, now we'll move on to velocity. Average velocity is always distance over time. Let's make this really easy. Let's do 1 complete spin. What is the velocity for 1 complete spin? All right, well, if we know the radius, the distance it moved was the circumference of that circle. All right, so the circumference of the circle is going to be 2 pi r. Okay, so my distance is going to be 2 times pi times r. And whoopsie, I got to go to my better pen. Sorry about that. Let's write this so it'll stay. My distance equals 2 times pi times r. And then what's the time it's going to take to go around in a circle? Hey, let's just call that a capital T, or call it the period. So if I do distance divided by time, what I'll end up with is the velocity is 2 times pi times r, that's distance, divided by the period. So if the distance is once around, then the time has to be for once around as well. Now, the direction of that velocity is changing all the time. All right, so this is something new. So notice here, I did not call the velocity a vector. This is just the magnitude of the velocity. Okay, now often we just leave that off because when we talk about circles, it's just kind of a given that the velocity is changing direction all the time. Okay, so a couple things. Velocity is 2 pi r over t, and the velocity is changing direction all the time. Alrighty, moving on. We did time, we did velocity, now we're going to do acceleration. So let's have a quick look. I drew two velocity vectors here, all right, 1 and 2. And remember, acceleration equals velocity v2 minus v1. The other way we sometimes write this is delta v. Okay, so here's what I did. I went down here and I made a copy of these vectors. So notice something. Here's vector 1. I'm going to put that right over here. And here is vector 2. They're exact copies. So there's v2, and now I have to do minus v1. So let's remember something. What you do is you put the arrow at the other end. So watch. I'm going to turn that around. So there's negative v1. Okay? So I'm going to take v2 and I'm going to add negative v1 to it. Let me write the vectors on there just so we know what they are. There's v2 and there's negative v1. Okay, so I think I'll do my acceleration vector in red. The acceleration starts where I started and goes to the end. So there is a v2 minus v1. So notice it goes mostly down but a little bit to the right. So the acceleration between these two goes mostly down and a little bit to the right. There's a. All right, crazy thing. Notice something. It's pointing exactly towards the center. So I could do that right over here, and guess what? My acceleration vector would point to the center again. Craziness here. This is a big idea, folks. One of the huge ones. Acceleration, when something is going in a circle, points to the middle of the circle. Always. Okay? Acceleration points to the middle. Now, one more thing with acceleration. Okay? The magnitude of the acceleration. Now, I could do some algebra and stuff, but I'm not going to. I'm just going to hand you this. I don't often do that. The size of the acceleration equals v squared over r. Okay? So, let's put a box around that one. Acceleration equals v squared over r. That's magnitude. Okay, because remember, the direction's changing. It's always pointed towards the center. The magnitude of the acceleration is the velocity squared over r. Jump back to the last slide we did. Okay, we can calculate the velocity this way. Whoops, that's the magnitude of the velocity. Then all we need is r down here, and we can calculate the acceleration. Okay? So this slide, two big things. Acceleration's always to the middle of the circle, and its magnitude is v squared over r. All right, we're close. Hang in there. So we're going to do forces now. Have a look at Newton's second law. Let's notice something. We've been doing this a lot. If we have the sum of all the forces equals ma, let's just look at direction now. All right. If the sum of all the forces points, for example, to the right, then the acceleration has to be to the right. So let's turn it around. If the acceleration is to the right, what direction is the sum of the forces? Well, that's easy. It's to the right as well. So if my acceleration is right here, and I know that's a, when my thing is when my spinning whatever is right there, then what direction does the force have to be? Force has to be in exactly the same direction. So guess what? We just made the jump. When you're going in a circle, what direction does the force always point? All right. So here we go. That's this slide. Force is always to the center. And check it out. When he's spinning that thing, what's the only direction a string can pull? Well, I guess I just told you, it can only pull. So the only direction that string can put a force on that ball of yarn is right towards the center, because you're spinning something around on the outside and the string is holding it in. Okay? All right. So let's go back to this guy here. I am going to show you now the acceleration vector. Check it out. The acceleration vector goes towards the center. All right? So the force is towards the center. So here's a crazy thing. This turntable, the spinning table, is pushing on the ladybug straight towards the center of the circle. Totally bizarre. All right, last thing, here we go. If we do an FBD of, let's say, our ball of yarn is right there. So I'm going to come over here, draw the ball of yarn. From the top, what direction is the force on that ball of yarn? It's right there. Okay? And that's the direction of the acceleration, right? But here's the idea. This free body diagram does not tell you enough alone to tell you that that's circular motion. All it's saying is there's a force pushing this way. Here's the crazy part. If we draw velocity this way, whoops, let me do a little bit better color for you. If we do velocity like this, and acceleration like this, so therefore the force is like that, all right, the force is this way too. I want you to notice something. The velocity and the force and acceleration are always perpendicular. So if you have acceleration perpendicular to velocity always, or force perpendicular to velocity, you will always have circular motion. All right? So even up here, notice what's going on. We have acceleration and force pointed towards the center. And what direction is our velocity? Whoopsie. It's perpendicular. All right? So, last thing. Velocity, force, and acceleration are always perpendicular. Okay? So, how do we do? Oh, that was a little long. Here is your video lecture problem. You get to work out all these things. All right? And that'll be it. Hope you enjoy yourself. Thanks for coming today. I appreciate you being here.